So it's a pleasure to have Marco Hufnagel. Hope you said your name correctly there. He's just moved to University Libre de Bruxelles in Belgium, and we're telling us about updated BBN constraints and electromagnetic decays of MeV-scale particles. So there's an hour. I will let you know when you're 10 minutes away, but usually the seminars do tend to run a little bit over if there's a good discussion in the middle.
Okay, great. Yeah. So yeah, hello everyone. Thanks for joining, and of course, thanks for the invitation. So I'm currently a postdoc at ULB in Brussels, and I'm going to talk about updated BBN constraints on electromagnetic decays of MeV-scale particles, which is work based on essentially these three papers over here, which have been published in collaboration with Paul Frederick Depter and Kai Schmidt-Hoberg back when I was still at DESY. So in order for you to know what to expect, let's start with a rough outline. So first of all, I'm going to give an overview and an introduction to Big Bang nucleosynthesis. So to make sure that everyone is on the same page, I'm going to tell you what BBN is, what actually happens, and how these events can be used to constrain different BSM physics scenarios. And then afterwards, in the second part of the talk, we're going to use this knowledge in order to derive constraints for a certain extension of the standard model, namely one where the standard model is extended by a dark sector that involves particles with electromagnetic decay channels. And while we discuss this particular model, we will come across a term of photo disintegration and see that it's a quite powerful effect. And this effect has been known for a long time and can lead to very stringent limits, but so far there hasn't been any public code in order to calculate these limits. And this is what we recently published with our code ACROPOLIS, which can essentially take account for this. And in the end, I will also give a brief overview over this code and tell you how you can use it on your own. Okay, starting off with the introduction. So Big Bang nucleosynthesis essentially is a term that's used to describe an early epoch in the expansion history of the universe, when the universe was between a second and roughly 10,000 seconds old. And this corresponds to temperatures in the MeV to keV range. And these temperatures were special in the sense that the universe has already cooled down enough in order to allow for stable nucleons. So neutrons and protons were populating the universe, but the universe was also still hot enough in order to allow for nuclear fusion reactions between these nucleons. So BBN really was a time when the first light nuclei like deuterium or helium were formed via nuclear fusion reactions of protons and neutrons. So if you take a look at these slice of the full reaction network that I pasted here, then you can see that, for example, neutrons and protons fuse to deuterium, which is then fused to even heavier elements like tritium or helium. And if you map the different elements that were created during this time onto the periodic table, then you find that these are mainly light elements that were created. So everything from hydrogen up to beryllium. To be fair, there are actually also some heavier elements created like nitrogen or oxygen. However, if you compare their abundance during BBN with what's later produced in stellar nucleosynthesis in stars, then it's essentially negligible. So the elements that I marked here are really those that are primarily produced during Big Bang nucleosynthesis. So now the cool part about BBN is actually that you can precisely calculate the amount of the different nuclei that were created during this time. And for this, you have to write down and solve the appropriate Boltzmann equation. So let's assume we have this quantity Yx, which is the number density of the nuclei x divided by the number density of all baryons, so something like a mass fraction or an abundance. And you want to know the variation of this quantity with respect to one of these reactions from this network, which we call R. Then, of course, this variation is proportional to the rate of this reaction, gamma R, and then also to the abundances of the initial state particles, because if there are no initial state particles to initiate the reaction, of course, then the variation would be 0. And of course, this is only one reaction. So if you want to have the variation with respect to the full reaction network, you have to sum over all reactions that involve this particle X and weight the different terms with a plus sign if the reaction creates X and a minus sign if it destroys X. And then finally, one last thing that you have to take into account is the fact that Boltzmann equations are fundamentally equations in time, while quantities like these rates are fundamentally measured as functions of temperature. So you also need to account for the relation that actually relates time and temperature in the early universe. And this is encoded in this time-temperature relation, dt over dt, which you also have to take into account in this equation. So overall, this then gives you a coupled set of nonlinear differential equations for the different abundances, which you can essentially solve using your favorite tools. And if you do this, you get something similar to this. So here I show the temporal evolution of different abundances in terms of some products and ratios that can later be easily compared to observations. So here in solid red is helium-3 relative to deuterium, blue is helium-4, and green is deuterium relative to hydrogen. And what you can see is once BBN starts at around 1 second, then these elements get rapidly created and then partially transformed into each other. But then at some point, the universe had cooled down enough in order to drop below the different nuclear fusion reaction thresholds. And at this point, the different abundances essentially get locked in because there are no reactions taking place anymore. And then these reactions stay essentially constant. And the cool part about this is that these, in the standard model at least, these abundances actually stay constant even until today. So what you could do is you could go out and look for astrophysical environments that have a low metallicity, so which means a low admixture of heavier elements from stellar nucleosynthesis, and then measure the abundances in these environments and then compare them with these theoretical predictions. And if you do this, you actually get a remarkable agreement. So these observations here are in dash dotted. And for deuterium and helium-4, you can see that these lines are basically completely on top of each other. And actually, you get an agreement better than 2 sigma for these two abundances. For helium-3, on the other hand, you end up a little bit too low with your prediction, but this has to do something with the way that this ratio is actually measured, because it's hard to find environments with a very low metallicity in this case. However, you can show that the environments that you measure this in can only increase this value. So as long as your theoretical prediction is below the observation, you're also fine. So this is also in agreement with observations. There is one notable exception, however, and this is the abundance of lithium-7. So I show here the abundance of beryllium-7. However, beryllium later decays to lithium-7. So essentially, the abundance of beryllium-7 later becomes the abundance of lithium-7. And here the problem is that the theoretical prediction is around a factor of 3 larger than what you actually observe. And this is known as a lithium problem. And it's, even though it has been around for quite some time now, the community is still struggling to understand and to explain this phenomena. So currently, the approach is most of the time to neglect lithium-7 when you calculate constraints and only focus on the different other elements. However, I still wanted to briefly show it here because we will later in the second part also discuss a possible solution to this problem, and then it's good that you already know that it exists.
So question, I have a question.
Sure.
So to make the comparison between observations and predictions, you have to assume a baryon to photon ratio. So what do you use, the CMB value?
Yes. We use, in this case, we use the CMB value, and then later when we do BSM physics, then yeah, we take, I mean, from the values that you obtain, we take the best fit value from the CMB. Yeah.
Okay. Yeah. Thanks.
You're welcome. Yeah. Okay. But if you basically don't consider the lithium abundance, then this is a remarkable achievement, right? A remarkable agreement and a remarkable achievement of the standard model of cosmology. However, one thing that you have to keep in mind is that this calculation has been done purely in the context of the standard model, so without any notion of dark matter at all. However, we know that dark matter exists, and it might potentially even come accompanied with a full-fledged dark sector. So one question definitely is, okay, if I add an additional dark sector, are there any effects that might spoil this beautiful agreement? And the answer to this is yes, there's actually a lot of stuff that can go wrong. And this is something that I would like to talk about in the next few slides. So first and foremost, one effect that you always have to consider is a change in the Hubble rate. So as I told you on the first slide, the Boltzmann equation for the different abundances critically depends on the time-temperature relation, which in turn is proportional to the Hubble rate, so the expansion velocity of the universe. This is rather intuitive because if the universe expands faster, then it also cools down faster. And the Hubble rate is essentially determined by the total energy budget of the universe. So if you only have the standard model, then the Hubble rate is essentially proportional to the square root of the energy density of the standard model. So you end up with a certain expansion velocity, and you end up with the abundances that are compatible with observations. However, if you now add an additional sector into the equation, a dark sector into the equation, then this dark sector comes with its own energy density. So you have to add it to the Hubble rate. So your expansion velocity becomes larger and your universe cools down faster. So you might reach these different nuclear reaction thresholds faster and therefore end up with abundances that are no longer compatible with observations. So what this tells you is essentially that there's only a certain amount of energy density that you're actually allowed to add to the one of the standard model in order not to spoil these different abundances. Okay, so besides the Hubble rate, another important effect is actually the effect of entropy injection. So usually in the standard model, when people calculate the time-temperature relation and get out that it's proportional to the Hubble rate, they use the fact that the entropy in the standard model is conserved. However, you might now consider a dark sector which can decay into electromagnetic radiation. And then, of course, this dark sector injects entropy from the dark sector into the standard model sector, meaning that this assumption is no longer justified. And if that's the case, you have to use a more general approach in terms of the second Friedmann equation, which tells you that not the entropy, but the total heat in the universe is conserved. So if there is a certain heat flow into the standard model, it has to come from the dark sector and vice versa. And if you use the second Friedmann equation instead to derive the time-temperature relation, then you also get this term proportional to the Hubble rate, but you also get an additional term which involves the volume heating rate of the dark sector. This is also rather easy to understand because, I mean, when the universe cools down, this essentially means that the temperature of photons becomes smaller and therefore the number density of photons becomes smaller. However, if say you have some dark sector states which just constantly inject additional photons into the dark sector bars, then of course the number density of photons drops slower and therefore the temperature of the standard model drops slower. So this is essentially encoded in this additional parameter. And one,
hey.
Yes, sure.
Sorry, I have a question about the Hubble rate. So you're saying that we're only allowed to have some amount of dark sector energy density, but what is the relation of the additional energy density with the lithium problem? Is it known that it makes the situation worse, or could it potentially solve the lithium problem?
Sorry, say again, what is the relation between the energy density?
Yeah, the additional energy density and the lithium problem. Is it any hope that the additional energy density can help alleviate the lithium problem?
I mean, the problem is that everything that you try to solve the lithium problem with, you can add a certain amount of energy density to the standard model and then end up with the correct lithium abundance. This is possible. However, you will always also end up with the wrong deuterium and helium-4 abundance. This is always a problem. So every time you try to do something to change the lithium abundance, which also affects the different other abundances, you're basically out of luck because deuterium is rather well measured. So if it also affects the deuterium abundance in some way, you might end up with the right lithium abundance and still be excluded by the other abundances.
I see. Thank you.
As far as I know, yeah, you're welcome. As far as I know, just by adding stuff to the Hubble rate, it's not possible to solve the lithium problem.
And another question, just kind of very basic. When you say that it accelerates and it contributes to the Hubble, this has to be in thermal contact with the standard model, or no?
No, it has not. This is
so if it has its own energy density completely secluded, it's still contributing.
Yes, it's also. I mean, this is also basic. Comes from the Friedmann equations, right? Where you just you can put whatever energy density in there. It doesn't have to be in thermal contact at all. Yeah. Okay. Yeah. So regarding this entropy injection, there's actually one quantity which is directly affected by this, and this is the baryon to photon ratio. So from CMB measurements, we know that the baryon to photon ratio at the time of the CMB is something like 6.1 times 10 to the minus 10. However, if you now go on and assume a dark sector particle, which can decay into photons, for example, and this decay happens between BBN and CMB, then during this decay, the number density of photons is actually increased, which means that the baryon to photon ratio is actually decreased. So this means if this decay happens before CMB, then you also have a larger baryon to photon ratio before CMB, and therefore also potentially during BBN. And this larger baryon to photon ratio, again, can lead up to completely different abundances that are no longer compatible with observations. This is especially because the deuterium abundance is very sensitive to the actual value of the baryon to photon ratio. And for the standard model value, which is well in agreement with observations, you actually use 6.1 because there's nothing that can change it between BBN and CMB. Okay, so 2 done, 1 to go. So the last effect that I would like to talk about is the effect of photodisintegration. So usually what happens in the standard model when these reactions are practically freeze out is that the average energy of the photon bars in the universe has no longer enough energy in order to destroy the previously created elements. And therefore these elements basically get locked in. However, you might consider a dark sector particle which has a mass at around the MeV-scale and which decays into 2 photons. And if this decay is non-relativistically, then this injects 2 monochromatic photons which also have energies at around the MeV-scale. And these are non-thermal, so they can have energies that are higher than the one of the thermal background photons. So this means even though the thermal background photons are no longer capable to disintegrate elements, these photons can. So what actually can happen is that even though you're fine after standard Big Bang nucleosynthesis, at some point you can inject these non-thermal photons, which then start to disintegrate, for example, deuterium. And therefore, even though you're fine after BBN, at some point you basically get abundances that are vastly different from observations. And again, this does no longer match, and this parameter point would essentially be excluded. So overall, what this tells us is that BBN is a very powerful probe to constrain different BSM physics scenarios, simply by demanding that the additional effects that you inject do not alter these primordial abundances by too much, so that they are still compatible with observations. And since this is such a powerful tool, a lot of people have already used it before. However, we were mainly interested in a very special case, namely the case of MeV-scale particles or dark sectors, like it says in the title. And this scale is rather special because here all of the different scales are approximately of the same order. So the mass of the dark sector particles is similar to the temperatures relevant for BBN. So you might transition from the ultra-relativistic to the non-relativistic regime directly during BBN, which can make the kinematic a lot more difficult. And also the mass is very similar to the thresholds for these different photodisintegration reactions, which essentially tells you that all of the different effects that I talked about have to be taken into account in one calculation in order to get consistent results in the end. And this is actually also what we do for the constraints that I show in a few minutes.
Yeah, but so I have a question on here.
Yeah, sure.
Yeah, so basically what you're saying here is if you have this other dark matter particle that's decaying, you could produce these the helium and the deuterium in abundance and then have this particle just destroy it to get it down to the observed values, right? For instance.
Yes. And this would also be possible, but I don't think that we found any parameter points where this actually happens.
Because the question then is, could you then just do that and maybe you could fit everything to the lithium abundance and then have something destroy the overabundance in these other nuclei?
Mm-hmm. I mean, yeah, but then the question is, but the problem is that you then also would start to destroy a little bit of lithium, right? I mean, it's always difficult to just destroy one without destroying everything else.
Yeah, but maybe because there's not that much lithium, you won't destroy as much. I don't know. Anyway, it was just a comment. Sorry, I didn't mean to. Yeah,
I mean, we can discuss this a little bit more in detail. It's just from the top of my head, I don't have a real answer to this. But actually, we will, when we discuss a solution to the lithium problem a little bit later, we will make, I mean, something that's a little bit similar, but not quite. But maybe we can then come back to the discussion if you have.
Okay. Yeah. Thanks.
Yeah. Yeah. Okay. So this is a special scale, and we have to take everything into account. Yeah. So now that we know what actually can happen, let's roughly go over the calculation that you have to perform in order to get the abundances in the end for a certain BSM physics scenario. So ultimately, what we want to do is we want to start from here. So with a certain Lagrangian with certain parameters, and for each parameter combination, we want to calculate the abundances in the end. And then depending on whether these abundances match the observation, we can then deem a certain parameter combination excluded or allowed. And therefore, we can then derive constraints in different parameter planes of this for this Lagrangian. So in order to go from here to here, the first thing that we actually have to do is to solve the Boltzmann equation that I showed you in the beginning, but this time in the presence of an additional dark sector. So for our purposes, these different reaction rates actually remain unaltered. This might change if you inject hadronic states, but this is not something that we're interested in right now. So this remains the same, and we have to deal with changes to the time-temperature relation. And as I told you before, this relation gets modified in two different ways. So once it gets modified directly via the appearance of this volume heating rate, and then it also gets modified indirectly via an additional contribution to the Hubble rate. So in order to determine this time-temperature relation, what we need to know is the evolution of the dark sector. So we need to know its energy density, its heating rate, and its pressure, and so on. And usually the way you do this is by solving the system of Boltzmann equation for the different dark sector states. However, this is rather model dependent because you have to know what states are in your sector and what interactions do they have. And here I would like to give a more model independent overview. So I would say that for now, we just assume that we solved this equation and got the different quantities for the thermal evolution. And later, when we come back to some actual models, we will take a closer look at these actual Boltzmann equations. But if we have the evolution, we can plug everything into the time-temperature relation and then solve this equation. And we do this by using the public code alter BBN, which we modified in such a way that it actually can take a modified time-temperature relation. And this code then gives us the abundances at the end of BBN for this dark matter scenario. And if you don't have photodisintegration, then that's basically it. These are the abundances that you can compare with observations. However, if you have photodisintegration, then you have to do two additional steps. So if you have a particle that injects non-thermal photons, then what actually happens is that these non-thermal photons do not immediately disintegrate the previously created nuclei, but instead they first undergo an electromagnetic cascade. So for example, one of the photons from the decay can scatter with a thermal background photon and then create two non-thermal photons with a slightly lower energy. So this means even if you inject monochromatic photons initially, due to this cascade reaction, you ultimately create a continuous spectrum of non-thermal photons. And you first have to actually calculate the spectrum. And to do this, you have to solve the so-called cascade equation, which essentially is also just a Boltzmann equation with some different approximations. And this cascade equation takes the rates and differential reaction rates for these different cascade reactions and also the injection terms for the injection of these particles, and then in the end returns the continuous spectra that result from this cascade for the different standard model particles, so photons, electrons, and positrons. And we solve this equation by our own public code, ACROPOLIS, which I will tell a little bit more about at the end of this talk. And then finally, when you have this non-thermal spectrum, there's one last Boltzmann equation that you have to solve. And this one is very similar to the first one in the sense that variation is proportional to initial abundance times rate. But this time, the rate is actually given by the photodisintegration reaction. So cross-section of the different reaction times the non-thermal spectra integrated over all energies. And then you can take these abundances as an initial condition for this equation with these non-thermal spectra that you solved before. And this will then, by solving this, give you the abundances at the end of photodisintegration, and you can compare them with observations and see what parameter point are excluded. And this is the rough procedure that you can actually apply to a lot of different BSM physics scenarios. So having this down, let us now take a look at some more concrete example. So in this section, we will consider an actual extension of the standard model by a dark sector that involves two additional particles, namely a dark matter candidate chi, which has a mass at around the GeV scale, and also a dark matter mediator phi. So this is essentially the particle from the title, which has a mass at around the MeV scale and which features non-trivial interactions with the standard model in the sense that it can decay into electron-positron pairs or into photons. And regarding the thermal evolution of these particles, we assume that at very large temperatures, the dark sector is in equilibrium with itself, but not necessarily with the standard model, which we incorporate by a temperature ratio zeta. And then at some temperature TCD, so decoupling, these dark matter particles decouple from each other. And while the dark matter candidate makes up the correct relic abundance afterwards, the mediator starts to redshift, potentially becomes non-relativistic, and then at some point decays. And this decay can happen either during BBN or during the times that are relevant for photodisintegration. So what we only need in order to apply the procedure that I described before is the thermal evolution of the sector for the time-temperature relation. And fortunately, since the dark matter candidate has a mass and energy density that's extremely suppressed during BBN, we're actually only interested in the evolution of the mediator here. So what we really want to know is the thermal evolution, so the energy density, heating rate, and pressure, and so on of this mediator. And as I told you before, the way to do this is by solving the appropriate Boltzmann equation for this setup. So the Boltzmann equation essentially describes the temporal evolution of the phase-space distribution function of f due to different effects that are relevant in this scenario. So one effect that's relevant is actually this dilution term. So this describes the change of f due to the expansion of the universe and therefore is proportional to h. And the other important effect is the decay and the inverse decay of the mediator. So either it's decay into 2 standard model particles or it's creation from 2 standard model particles, whereby this f term over here encodes the decay and this f bar here encodes the inverse decay, whereby this bar here means this is the phase-space distribution function that the particle would have if it was in thermal equilibrium with the standard model. So this means Bose-Einstein distribution with the same temperature as the standard model. And then there's also this kinematic term here in front, which essentially describes the kinematic of the decay. And if you write this down, then things get a lot more complicated. However, I promise you can break it down into individual chunks, which are actually quite easy to understand. So if you neglect everything else and just look at the first term over here, then essentially you have your usual decay law for non-relativistic particles. So something like variation is proportional to 1 over lifetime times value. So just your usual decay law. However, this is for non-relativistic particles, and our particle can also be ultra-relativistic. So you also have to account for an additional gamma factor, which might change the lifetime in the co-moving reference frame. And then in addition to these relativistic corrections, you also have to take into account quantum corrections in terms of Pauli blocking and Bose enhancement. And you don't have to remember this part. It's just this term is larger than 1 if you decay into photons because you have Bose enhancement, and smaller than 1 if you decay into electron-positron pairs due to Pauli blocking. So, I mean, this all looks a little bit complicated, but the idea of the slide is not that you actually remember all of these different terms. It's just to show you that we actually take into account all of this, and all of these different effects are actually also shown in the included in the final constraint that we get and that I will show you on the next slide. And then you can just solve this equation and get the energy density and so on, get the time-temperature relation, and then apply the procedure that I showed you before in order to get the constraints in the end. So let's now come to the constraints. So first of all, I would like to show you the constraints in the plane that's spanned by lifetime versus mass. And here I'm looking at a scalar mediator. So this means degrees of freedom. So this G is not a coupling constant. It's just 1 degree of freedom. And the scalar mediator decays exclusively into photons, decouples at a temperature of 10 GeV, so much before BBN, and at the time of decoupling has a temperature ratio of 1, so the same temperature as a standard model. But this is just a benchmark. It doesn't mean that it was actually in equilibrium with the standard model. And here, besides the overall constraint, which is the dashed black line here at 95% confidence level, I also show the regions of parameter space that are excluded due to individual elements. So here in this pinkish region, for example, your helium-4 abundance is too high. In this grayish region here, your deuterium abundance is too low, and so on. And then there's also this dashed black line here, which shows you the overall constraints if you would neglect spin statistics and inverse decays. So this is actually rather different. So it's important to take this into account. And then finally, this orange line here is an additional constraint from the CMB, which is just due to the fact that in our model at the time of the CMB, the effective number of neutrinos might be too low, which then gives you an additional constraint from the CMB, which is, however, decoupled from one of the BBN. It's just our calculation basically gives this for free, so we could just as well put it here. And the interesting part about this plot is that you can actually divide it into 2 very different parts, right? So here, down here for small masses and lifetimes, you essentially get a straight line and exclude small masses independently of the lifetime. While here for large masses and lifetimes, you get a more well-defined slope where the bounds actually become stronger with the mass. So in order to understand why there are so different regions of parameter space, it's actually a good idea to just separate the parameter space along this line and look a little bit closer at the kinematics in these different regions. And if you do this, then you find that in this region of parameter space, the temperature of the standard model at the time of the decay is actually much larger than the mass of the particle. So if the particle would be in equilibrium with the standard model, it would still be ultra-relativistic. And in this region over here, it's actually the opposite case. Here, the temperature at the time of the decay is much smaller than the mass of the particle. So here, if it was in equilibrium with the standard model, it would already be Boltzmann suppressed. So in order to understand why this makes such a huge difference, let us take a look again at the Boltzmann equation, but this time not in terms of the spectrum, but in terms of the number density n. And here I've absorbed all of these quantum statistics and relativistic corrections in this effective gamma factor. Actually, this equation is not quite correct, but it kind of gives you the right idea and is easier to explain. So I think it's worth to make this small sacrifice. So what this equation then tells you essentially is that once this term on the right-hand side becomes large compared to the term with the Hubble rate, then essentially the solution to this equation is just n is equal to n bar. And bar here, remember, thermal with the same temperature as a standard model. So this means once this condition here is met, the particle effectively gets thermalized with the standard model heat bars. And if you do the math, then you find that this relation here is approximately satisfied at around the lifetime of the particle. So what does it mean? Well, it means that once a particle reaches its lifetime, it doesn't simply decay, but instead it gets effectively thermalized with the standard model heat bars. And this process actually has two very different effects in these two regions of parameter space. So to understand this better, I made this small sketch here with the number density as a function of temperature. And here in red, I show the actual number density of the mediator without decay, so just redshift. And here in purple, I show the number density that the mediator would have if it was in thermal equilibrium with the standard model. And here, for example, you see the Boltzmann suppression. If you would reach the mass of the particle, it would get Boltzmann suppressed. And if this particle would not decay, it would just redshift until eternity. So, however, we know that it has to decay at some point. So let's just assume that this decay happens at around this time. So when in the standard model, it would already be Boltzmann suppressed. Then what the Boltzmann equation tells you is that around the lifetime of the particle gets thermalized with the standard model. So the red curve is forced onto the purple curve, which means that the abundance essentially vanishes because the red curve gets forced onto an already Boltzmann suppressed distribution function. And this is the traditional decay scenario where essentially at the time of the lifetime of the particle essentially vanishes. And this is the case in this part here of parameter space. However, what if we now take a look at the exact opposite case? So if we decay when the particle would still be ultra-relativistic in the standard model, well, then again, the Boltzmann equation tells you that red curve is forced onto the purple curve. So in this case, even though the particle reaches its lifetime, it does not vanish, but instead it even gets created. So there's a certain freeze-in process which creates these particles via inverse decays. And the particle only vanishes once it becomes Boltzmann suppressed, since it afterwards is in thermal equilibrium. So in this case, the particle actually does not vanish when it decays, but only very much later at around the mass of this particle. And this is actually what happens in this part down here of parameter space. So with this set, we can now understand basically everything of this plot. So in this region over here, the particle always thermalizes with a standard model, and it completely thermalizes with the standard model heat bars. And since the lifetimes are so small, this thermalization always happens before BBN starts, which means that in this region of parameter space during BBN, you always have to deal with an additional thermal particle. And usually that's excluded. And the only way to get around this is by making the particle heavy enough so that it becomes Boltzmann suppressed sufficiently long before BBN. And what you find is that you need a particle that's heavier than 0.45 MeV in this case. So everything below this is essentially excluded because you would just have an additional relativistic particle during BBN. And then in this region of parameter space, you have a more traditional decay scenario. And here your particle actually vanishes at the lifetime. And there the constraint comes from just from the question, okay, you want your particle to decay sufficiently long before BBN so that it doesn't spoil anything during BBN. And as I told you, BBN starts at around 1 second, maybe a little bit earlier. And what we find is that the particle has to decay before 0.1 second in order to be safe for all masses.
And
However,
so
yes, sure.
So what happens then if I increase the mass? It just plateau out? Is that what that curve will do?
Yes, it would just plateau out here at some point.
So I could go all the way up to 100 GeV, and
yes,
I think people in the past were looking at, say, NLSPs decaying during BBN. So these would be non-relativistic. They decay to a gravitino, and I think they were busting up the BBM abundances as well. So I guess it has to match onto this curve as well eventually.
Yeah, probably. Yeah. I mean, I haven't looked into it, but I guess so. I mean, yeah.
I guess it depends on the final state of the decays of phi or whatever particle you're
considering.
considering.
That's true. I mean, yeah. I mean, if you're too heavy at some point, they decay into hadrons, then.
Oh no, with these particles were decaying into photons. It was photon gravitino, so there were photons around. Yeah.
Yeah.
So, but you're exploring a much you're exploring a much lighter mass range, and you're pointing out these new constraints.
Yeah. Right.
Yeah.
Okay, so you have these different regions, and I made it look like there's actually a very clear separation between these regions, which, however, is not really the case, in the sense that even though you have a full freezing over here and you don't have a full freezing in this region, you can still have like a partial freezing in this region. And then this freezing still produces some particle, but it's not efficient enough and actually bring it into thermal equilibrium or produce an efficient amount of particles. And for example, you can see this in this little dip over here, which actually comes from freezing and photodisintegration, which is quite funny, and which I will discuss a little bit in more detail in the next slide. So since there are two very different phenomenological regions in this plot, it might be interesting to see what happens if I actually reduce the temperature ratio. So what happens if I reduce the initial abundance? It makes the freezing ever more important. And in order to discuss this, here I show essentially the same plot, but with different temperature ratios at the time of decoupling. So the green curve is the one that I showed you before. That I showed you before, with a temperature ratio of 1. And if you go down here, the temperature ratio becomes larger, and up here, the temperature ratio becomes smaller. And naively, you would say, okay, if I decouple ultra-relativistically, then my abundance is proportional to temperature ratio cubed. So if I just make it arbitrarily small, then my initial abundance would be arbitrarily small. So at some points, the limits would just vanish. However, this is actually not what happens in most parts of parameter space. And this is because if you look at this region down here, then I told you that here you always have an effective thermalization before BBN. So here you always reach a thermal abundance, and this doesn't matter what your initial condition is, because you always end up with the same abundance long before BBN, and therefore the limits will always be the same in this region of parameter space independently. So your initial condition is essentially rendered meaningless in this region. So you cannot reduce these limits here any further. And then in this region where you have a more traditional decay scenario, there you actually see that the limits become smaller. However, there's also some dip over here. So it seems like there start some islands to form, which so that in this region of parameter space, you also cannot reduce the limits indefinitely. And this is actually due to partial freezing. So in this region of parameter space, you have a certain partial freezing, and this freezing creates enough particles so that you're getting constrained from photodisintegration, because photodisintegration is capable of constraining even very small abundances, as we will see later. So in this region, you also get some islands, and you cannot reduce the limits indefinitely, even if you reduce the number density completely. So if we take this to the limit, so essentially it takes a temperature ratio to 0 so that we only have freezing, what you would assume is that this limit would remain and that you would get some islands over here. And actually, that's exactly what you get. So this is pure freezing, no initial abundance at all. And there you actually see the exact same case. So here you always have a thermal abundance, limits remain unchanged. And here the partial freezing is always strong enough in order to get to some limits from photodisintegration independently of the lifetime. Okay, so I think we covered this part of parameter space enough. So now I would like to show you a different part. So here I show the initial abundance of the mediator at the time of decoupling at 10 GeV for different lifetimes, and the different colors are different masses. And I actually like this plot a lot, because in this plot you can really see that all of the effects that I talked about earlier are important and can be dominant for different ranges of lifetimes. So if you're at very low lifetimes, then your limit dominantly comes from the additional contribution to the Hubble rate, and you get this line here basically. However, if you then go to larger lifetimes, then at some point entropy injection and the baryon to photon ratio become important, which is why your limits start to become stronger in this region here of parameter space. And then if you go to even larger lifetime, then at some point photo disintegration kicks in and your limits become a lot stronger. And here you can really see that photo disintegration is able to probe even very small abundances, 9 orders of magnitude below the photon abundance. And then depending on what lifetime you have, the disintegration channel might be different. So in this region, you dominantly disintegrate deuterium, while in this region here, you dominantly disintegrate helium-4. And we also have these kind of drops over here, which come from partial freeze-in, which is why it doesn't really is monotonous here in this region. Yeah, but I like this plot a lot because here you can really see that all of the effects that I talked about before really have to be taken into account consistently so that you really end up with the overall limit in the end, especially in these transition regions. Okay, and then finally, the last part of the last parameter plane I would like to show you is this one. So this is essentially the same y-axis. Initial abundance is the time of decoupling, but this time versus the mass and for different lifetimes. And this plot is especially interesting because it should directly tie into the freeze-in plot that I showed you before. So essentially, if I make the initial abundance arbitrarily small, I would at some point reach just a normal freeze-in. So this means all of these pillars here, which essentially exclude arbitrarily initial conditions, we should be able to map these pillars to the respective regions in this freeze-in plot. And this is actually what you're able to do. So for example, here for small masses, these large pillars can be mapped to this region over here where the particle is just thermal. And then in this region over here where photo disintegration is relevant, you get these pillars over here. They are essentially in these different islands, which then cause an exclusion for arbitrarily small abundances. And here you can also see that really photo disintegration is responsible for these islands over here. And what's also interesting about this plot is that you can actually see the different disintegration thresholds for the different photo disintegration reactions. So for example, in order to disintegrate deuterium, you need a photon with at least 2.22 MeV. So since your particle decays into 2 photons with the same energy, this means that your particle needs to at least have a mass of like 4.44 MeV. And this is why only here the limits from photo disintegration and deuterium disintegration start to become important. So you see this threshold over here. And then you also see the threshold here from helium disintegration, which has a threshold of 19.81 MeV and therefore should become important at around 40 MeV mass. And this is this additional kink over here. Okay, now the interesting part is even though this plot might you believe that deuterium has the lowest disintegration threshold, that's actually not the case. There's one element that has a smaller disintegration threshold, and that is beryllium-7, which has a threshold of 1.59 MeV. And now if you remember, I told you in the beginning that beryllium is essentially the main cause for the abundance of lithium-7, simply because it at some point decays into lithium-7, and then you end up with a final lithium-7 abundance. And I also told you that the theoretical prediction for lithium-7 is too large compared to observations. So there might be a potential idea to exploit this disintegration reaction in order to destroy enough beryllium to eventually end up with the correct lithium abundance. And here the interesting point is that essentially if you are in this mass range over here, so between these 2 photo disintegration thresholds, then you only can disintegrate beryllium while all of the other elements essentially remain unchanged because you do not have enough energy to destroy them. So if you are exactly in this small mass spot, you might be able to destroy enough beryllium and therefore lithium in order to solve the lithium problem. And in order to check this, we made a finer graded scan in this part of parameter space. And this is when we got these results over here. So this is initial abundance versus mass. So same plane for different lifetimes in different colors. And these white shaded regions are the regions that are already excluded due to BBN and other elements. However, in this colored region over here, you actually get the correct lithium abundance within 2 sigma. So you can see that there actually are some parts of parameter space in this very narrow mass window where you can destroy enough beryllium-7 without spoiling the other elements, so that you still end up with the right abundances basically for all elements, including lithium. However, I have to make a remark here. So we were not the first to actually discuss this possible solution. So there was a paper in 2015 by Serpico who first brought this up, and there was also a recent paper by Kawasaki et al. Who elaborated this a little bit further. And in our paper, we also built up on this and brought this a little bit further. And especially we showed that there are actually concrete models with concrete Lagrangians, like, for example, axion-like particles, where in these models, you actually also can fulfill this and get the right lithium abundance. But unfortunately, in this talk, there's not enough time. Sorry, yeah?
So can I ask a question about that? Because so this phi will decay via dimension 5 terms. So what's the decay constant for this particular decay right in this window?
You mean for the axion-like particle?
Yeah. What do you remember the mass range, the mass scales for these decay constants?
Yeah, I mean, this is a good part about a virtual talk, right? Because I basically have all of the plots on my laptop. But I mean, since this is I don't know, a little bit off, so I would have to go out of the talk and show you a different plot. Maybe you can maybe you can remember this question until the end of the talk.
Sure, that's okay. Yeah.
When I'm done, I can show you the actual plots, and I don't have to guess. I can show you the actual plots. Yeah.
Okay, thanks.
Okay, yeah, you're welcome. Yeah. Okay, so much for this. Yeah. Let's now briefly, in the last part of this talk, talk about our public code ACROPOLIS. So from the limits you've seen so far, you essentially got the idea that photodisintegration can be quite powerful, especially since it can constrain very small abundances much below the photon abundance. So chances are that at some point you could need these limits for your own models or for your own evaluations. And in this case, what would you do? Well, you would basically look in our paper and try to extract the lines. But this is always a hassle because we probably don't have the right parameter combinations for you. So you have to do some interpolations. And it would be much better if you could just calculate this on your own. With a few simple clicks, just calculate the abundances at the end of photodisintegration for your own scenario. And the good news is that with our codes that we published, ACROPOLIS, you can essentially just do this now. So ACROPOLIS is open source software licensed under GPL3, which essentially can perform photodisintegration and calculate the abundances afterwards for a variety of different BSM physics scenarios. So it's written in Python, Python 3, of course, and it has a few dependencies. So NumPy, SciPy, and Number need to be present. But apart from this, you're essentially are ready to go. So just clone it from GitHub, and then with a simple command, you can essentially just calculate the abundances for a variety of different BSM physics scenarios. And there are actually 2 example models that we ship and that you obtain when you clone the repo for the case of dark matter mediators into electromagnetic radiation. So essentially the example that I discussed before, but also residual annihilations of dark matter particles into standard model electromagnetic radiation that's also included here. So this should already cover a lot of different physics scenarios, these example models. However, while developing ACROPOLIS, we also made sure that it's quite easy to implement your own models in case it's not covered by these example models. And I will also talk about this a little bit at the end. And yeah, and of course, it's now also finally on HepForge. So if you have any ethic concerns about cloning, so then you can just get it from HepForge instead, and you're basically good to go, because these versions should always match. Yeah, so let's now talk a little bit how ACROPOLIS actually functions, and then for this we have to go again over the process of photodisintegration, but this time I would like to focus a little bit more on what are actually model dependent and what are model independent inputs, so that you exactly know what you have to do when you implement your own scenario. So as I told you briefly before, photodisintegration essentially proceeds in 2 different steps. So once you inject these non-thermal particles from photons from the dark sector, then in a first step, these particles undergo an electromagnetic cascade reaction, which leads to a continuous non-thermal spectrum. And then in a second step, these non-thermal particles then undergo the actual disintegration reactions, which can destroy some of these previously created nuclei. So Regarding the first step, the important equation is the cascade equation. And this cascade equation takes as a first input the rates and differential reaction rates for these different cascade reactions. And actually, this input is model independent because it's just standard model particles, scattering of other standard model particles. So you can calculate it once, implement it once, and then forget about it. And if you use ACROPOLIS, you can essentially also forget about everything because it's already implemented and it doesn't change if you use a different model. And here we essentially put all of the different cascade reactions that we actually implement in ACROPOLIS, and you can find them scattered throughout various papers, but it was kind of complicated to collect them because the literature has quite a few typos and it was difficult to find what the actual right rate was unless you calculated it on your own. So this is why in our first paper regarding this topic, we actually made an appendix where we show all of the different rates and discuss all of the different typos, which now hopefully has no typos anymore and can be used for this kind of stuff. But as I said, if you just use ACROPOLIS, then this is basically none of your concerns. But if you want to look up the implementation, then you can go into acropolis.cascade in this package. There you find all of these reactions, and especially in spectrum generator, this is the class that actually solved this cascade equation. However, besides these model independent reactions, you also have a model dependent input, and these are the source terms for these different injections. So the source term is different depending on how you inject these particles. So if it's a decay or annihilation, then the source term can be different. So this really depends on your actual BSM model. So if you implement a certain model, this is something you have to provide. So keeping this in mind, we come to the second part, which is non-thermal nucleosynthesis. And here you have to solve this Boltzmann equations that I showed you before. And the model independent input here are the different cross sections for these photodisintegration reactions, which we take from an old paper of Brian Fields et al. And we implement all of these. And this is also model independent. So if you don't want to, you don't have to bother at all about these. But if you want to have a look at them, they are all implemented in the acropolis.nucl package, and especially in the class nuclear reactor. And in the class matrix generator is essentially the class which solves this differential equation, because you can just rewrite it in terms of a matrix equation and then easily solve it. However, there's also one model-dependent input, and this is actually the temperature range over which you integrate this differential equation. So this is essentially the temperature range for which photodisintegration is relevant. And this also can be dependent on your actual models. Because, for example, if you have a decay, then this is a very, very narrow temperature range, just around the decay time. However, if you have annihilations or something, then this can be more continuous, and you might have to consider a larger range of temperatures. So this is also something that you have to keep into mind, and therefore also something you have to provide if you implement your own model. Okay, a lot of talk about implementing your own model, but I also told you that you can essentially just run a lot of stuff with just one click. And for this, we ship with some example models. And here we'll go over the example model decay model, which is in this module, and which essentially comes with the executable decay if you just clone the repo. And this decay executable just takes 6 command line arguments. So this is basically for a mediator that decays into electromagnetic radiation. So just the same thing that I discussed in the second part of this talk. And you have to provide it with a mass of the particle, a lifetime, and then a reference temperature and the abundance of this particle relative to photons at this reference temperature, assuming that afterwards the abundance only redshifts. And then finally, the branching ratios into electron-positron pairs and into 2 photons. And then you can just, from your command line, call the script with the respective command line arguments, and it will calculate the non-thermal spectra, perform the non-thermal nucleosynthesis, and then in the end gives you the abundances after photodisintegration. And here, these are just for different input parameters from alter BBN, so that you have a way of approximating the theoretical error, for example. So if you just use these example models, and also for the annihilation model, then it's really just easy as this. And we also provide a scanning framework if you want to scan a whole set of parameter combinations. So for example, in this model, you could now do a full scan mass versus initial abundance, something in like 20 to 30 minutes, and you're basically done with it with the current implementation, but we're trying to make it faster over time. Yeah. But then finally, if you really want to implement your own model, so then you might think, well, it's not in ACROPOLIS, so it might be a little bit too difficult, so I don't do it. And with this slide, I basically just want to take the fear from you that it's really easy to implement your own scenarios in ACROPOLIS. And this is because we essentially try to hide most of the low-level implementation from the user so that the user doesn't come in contact with this, which essentially we've done in this class abstract model. So this has all of the low-level implementation, but you do not have to think about it too much. It's just if you implement your own model, say new model, you just have to inherit from this abstract base class, and then you inherit all of the low-level implementation. And the only thing that you have to do is basically provide these two model-dependent inputs in terms of some functions, abstract functions that you actually have to implement. And there it's also quite easy. So for example, these source terms are defined in these different underscore source functions. And in these functions, we allow monochromatic injection and also continuous injections. And you can just mix them as you want, however your models predict them. Then, for example, here you have a monochromatic injection of photons would be implemented in the source photon 0. And for electrons, it's here. And then you also have continuous spectrum parts where you don't have the 0, but the C over here, and where you also have to provide an energy instead of just a temperature, because, of course, this part also depends on the energy. And let's say, for example, you could just put here return 1, and the code would calculate this whole thing with a source term of 1, whatever that would mean in the end. But yeah, so essentially you just have to make implementations for these different source functions, and you have to give the temperature range for which you want to integrate this second differential equation. And therefore you have to implement this function temperature range, which just has to return a tuple in the end with minimal temperature and maximal temperature, and that's basically all. And from this abstract model then takes all of these functions that you implement and does all of the nasty stuff, so you don't have to worry for it. So if you want to see some example implementations, you can always go into acropolis.models, and there, for example, we also have implementations for the decay model and the annihilation model. And it's not a lot of code that you actually have to put there. You just have to do a little bit of physics in order to get these different source terms. Okay, this essentially also brings me to my conclusions. So what I've tried to show you in this talk is that the inclusion of additional dark sectors to the standard model can essentially influence Big Bang nucleosynthesis in many different ways, and therefore is a very powerful tool to constrain different BSM physics scenarios. And we especially applied this to the case of dark sectors with particles that can decay into electromagnetic radiation. And for the first time, we also included the effects of inverse decays and spin statistics, which can lead to vastly more stringent limits, especially for small masses, where you essentially exclude independently of the lifetime. But also in the more traditional regions, the limits can be very different from the naive estimate. So usually people assume if they don't want to do the full calculation, okay, BBN starts at around 1 second. So if I decay before this, I'm essentially fine. But we found that if you want to be fine for everything, that it's better to use 0.1 seconds in order to be, at least if you have a thermal particle. And then finally, I also showed you ACROPOLIS. So if you ever want to do photo disintegration in any of your projects, then this code essentially has you covered, and it's free. So just download it, try it out. And yeah, right now we're actually making a lot of changes. So the code is always improving. So the manual that you find on arXiv might not always be the most recent version. So it's always good if you have a more recent code than version 1.1 currently, maybe go to GitHub and take the manual from there. And then you already have the most recent manual for this. So yeah, but if you ever need to, just download it. And if you have questions, of course, you can ask me anytime, or any other member of the collaboration who wrote this code. And with this, I would like to thank you for your attention. And yeah.
All right, thank you a lot, Marco. You can give us some virtual applause. If there are any questions.
So, I mean, maybe I can come back to this question about the axion particles, right, and the lithium problem, which I basically postponed to the end of this talk. Okay, so, okay, well, this is all in terms of the lifetime. Ah, great. I mean, for the axion-like particle, what we essentially considered was we had a lifetime given by the coupling constant, a mass of the particle, and then also some reheating temperature, which essentially gives you the start when Primakov interactions, which are UV divergent, become relevant. And in this region, then we basically checked if we can solve the lithium problem. And here you can see that, for example, here in the plane lifetime versus mass, you can solve it in this region over here. So like 10 to the 8 seconds. And this is the plane lifetime versus reheating temperature. But I can also, we can also map this to an actual coupling constant. For this, I just have to, it's a question, do I have the same plot in both different things? I should have, I guess. Let me see. Yes, I have. This is lifetime. Well, of course, it's not on there. So 10 to the 4 seconds would be 10 to the minus 11, but it's quadratic. So you have to go to.
But you have the G phi gamma there, right? That can be thought of as.
Yes. No, I was just trying to map it because in the code we excluded lifetimes 10 to the 8 seconds, which is unfortunately not on this plot, but I cannot map it. But it should be something very small. I mean, it's 10 to the 8, then it goes quadratically, right? So it should be something like 10 to the minus 20 or whatever, if I'm not mistaken. But maybe I'm making a mistake in my rough estimate.
Yeah, I was just worried about that scale because that scale. Normally a dimension 5 term, you got to integrate out some physics to generate that scale, but that physics then might actually be also relevant during BBN. That's why I had the question.
Yes. But I mean, looking at this, the G should be rather large, so the scale should be rather high. So I think this shouldn't be a problem. So at least for the parts where you can solve the lithium problem.
Mm-hmm.
But I should be square root of the lifetime, right? The scale of G phi gamma. You were saying you're squaring something.
Okay, might also.
Take the square root.
Yeah. Okay. Yeah. This might also be, but we can agree that it's smaller than 10 to the minus 11, 1 over GeV. So then it's probably like 10 to the minus 15 or something. So higher lifetimes mean smaller coupling. So 10 to the 8 should at least be somewhere down here, like 10 to the minus 15 or something. Yeah.
Okay.
So the scale is very high and you probably won't need to worry.
Yes, I mean, the scale would be something like 1 over G, right? So it would be rather high.
Because normally for axions, I thought that the axions have to live longer than the age of the universe, right? So their decay constants are intermediate.
Okay, yeah, this is true, but in our case, the axion-like particle is not necessarily a dark matter candidate. So, I mean, you could have an additional dark matter particle, but it's just an axion-like particle which might decay before that. So it's not really.
I see, because you're saying that the mass is an independent. The mass for this particle is a separate parameter now.
Yes. Well, I mean, you could draw some lines in this parameter space for these different axion models, which I always forget these combinations of letters. And but here we actually have a parameter space that's spanned by 2 independent parameters.
Exactly. So I see. Yeah. That answers my question. And yeah. Thanks.
Okay, great. Yeah.
So I actually had a question when you say you can implement new models, your code does phi to be plus and minus and gamma gamma.
Mm-hmm.
I wonder, so first, I guess if you had branching ratios into muons or into invisible stuff, for example, in the case of a stereoneutrino, you'd get neutrinos always in the final state.
Yes, I mean, this would work because these neutrinos just don't do anything. So you would just, here, for example, you would just, I don't know, put a branching ratio into electrons of 0.5 and photons into 0. Then you would 0.5 into invisible states, and they don't.
But does it matter that this is a 2-body decay versus, for example, if I have some model, let's say people are interested in stereoneutrinos with a dipole coupling where HNLs decay to neutrino plus gamma. Would that go into your branching ratio to gamma gamma, or would I need a new implementation of that?
You probably would need a new implementation because in this case, No, let me see.
I guess the energy distribution of the photons will certainly be different, but
when the energy distribution is different, then you have to do your own implementation. Then you basically have to model a continuous source term which describes this energy injection.
okay.
I mean, but if you have one, yeah.
And the other question is also, out of the several mediators that people consider, I guess the one that is kind of, there are some constraints from BBN, but I think they don't touch really the region that people are usually more interested in, is L mu minus L tau, where you have some branching ratio to plus and minus, but it's very suppressed. And then you produce mostly muons. Would that be interesting here? I guess the muons could give you the photons for the photo disintegration.
I mean,
I don't know, maybe if the scale is too high for that.
I mean, I think it could be interesting, but the problem right now is that muons are not implemented. This is on our to-do list for version 1.2, or I don't know actually when we will implement it. I just started. It shouldn't be too difficult because the rates are essentially the same as for electrons, and you just have to take care of the decay.
But do you think it would be constraining for these models, or is it just a very suppressed process? Because I mean, I guess there's a requirement that your mass has to be hundreds of MeV. So that.
I mean, I would say for large lifetimes, this should potentially be relevant. But then if you, I mean, there's only a very narrow window where you can actually decay into muons without decaying into other hadrons, right? And once you decay into other hadrons, you get these constraints from hadron disintegration, which are also quite strong.
Yeah, but I guess in these models, you would always just decay to leptons because it's a leptophilic kind of force.
I mean,
but I'm just wondering if we can kill this region of G-2 for L mu minus L tau with this idea of photo disintegration, because.
I mean, it would certainly be constraining. However, I miss the intuition to tell you if it would be constraining enough compared to other stuff in this parameter plane. So maybe there are already other limits that are more constraining than this. So there's no guarantee that you would gain anything from this. But I mean, when we finally, hopefully at some point implement muons, if this doesn't take too long, then this essentially would be just, I don't know, you could run it once and you're essentially done, right? So then you can easily test.
Okay.
I have a simple question. So if the phi mass is sufficiently light, for example, much lighter than MeV, then I would expect that the decay products, the photons, will have too little energy to destroy the nuclei. In that case, then I would expect that the constraint will just go away no matter how long the lifetime is. Is that true? And how come I couldn't see it from the figures that you had?
Wait, let me see. So, I mean, if you here, you essentially only have photo disintegration constraints in this region of parameter space. Okay, so everything that's below this mass essentially comes from Hubble rate and entropy injection. So in this region of parameter space, if your mass is very low, there you would actually, the photons would undergo inverse decay and then produce a lot of these mediators, and then you end up with a thermal particle during BBN, and this then excludes you. But I mean, here you see that, I mean, photo disintegration essentially stops being relevant at 4.44 MeV, which is at this point here. And this line here comes from entropy injection. And you also see this in this plot here, right? I mean, if you go to smaller masses, you see that these different bumps essentially disappear. So here for 10 MeV, for example, you get a prominent bump from deuterium disintegration. But then if you go to 5 MeV, which is only marginally above the disintegration threshold for deuterium, then this bump basically goes away. So here you also see that photo disintegration becomes less relevant if you go to very small masses. But you will always have these constraints from entropy injection and the one from the Hubble rate. Yeah, not sure if this answers your question, but
yeah, that answers the question. Thanks.
Okay, yeah, you're welcome.
Any other questions? not, I'll stop recording.